Hello to you all. Welcome back to the differential equations tutorials. So we are going to look at the reducible linear coefficients to homogeneous functions. So I've told you that the first time you are given a first order differential equation, to find the solution, you must first check whether it's separable. If it isn't separable, check whether it is homogeneous. And if it's homogeneous, then you reduce it to separable. If it is not homogeneous, then you check whether it has linear coefficients. Okay, so if it has linear coefficients, then we have a way of reducing it to be homogeneous, and then we take it from there. Okay, so what do I mean by linear coefficients? Let's say I'm in my differential form where I have mxy dx plus nxy dy being equal to 0. And mxy and nxy are linear coefficients. So an example of linear coefficients will be, let's say I have a1x plus b1y plus c1 dx. And I have a similar one for my nxy. So I have a2x plus b2y plus c2 dy being equal to 0. Okay, so if it is of this form and my a1 b1 c1 a2 b2 c2 are all what constants, if they are all constants, we can then look at two cases on how to bring it into a homogeneous function. We are going to look at two cases here. So I'm going to write them, those two coefficients. Okay, I have my a1x plus b1y plus c1 being equal to 0, and a2x plus b2y plus c2 being equal to 0. So in our first case, we say that if a1 over a2 is not equal to b1 over b2, then we are going to just solve these two equations simultaneously to obtain a unique solution. Okay, so if I have this simultaneous equation and I solve, I'm going to get a solution which is x naught and y naught. Okay, because our unknown variables are two, x and y, so we are going to get x naught and y naught. Okay, and we are then going to let our x and y be capital X plus that x naught we got from our solution, and our y is going to be substituted with our capital Y plus y naught. Okay, if we do this and we substitute this values of x and y into our main differential equation here, this one here, it is going to be turned into a homogeneous first order differential equation. Then we proceed from there, and we then convert it to separable and find the solution. Okay, so in the next page I'm going to try an example to see how it works. So we have x minus 2y plus 1 dx. Let me write it well. X minus 2y plus 1 dx plus 4x minus 3y minus 5 dy equal to 0. So we have to check whether a1 over a2. Here our a1 is 1, our a2 is 4. And we have to check so we have a1 over a2 to be equal to 1 on 4. And we have to check whether it is equal or not equal to b1 over b2. b1 over b2 is negative 2 over negative 3. So you have 2 on 3. So they are not equal. Okay, since they are not equal, we are going to solve these two linear coefficients simultaneously. And that is outside the scope of this course. So we are just going to find the solution. I'm just going to write it. So we will get x naught to be 13 on 5. And I'll get my y naught to be 9 on 5. Okay. And in doing so, I'm now going to replace my x will now become capital X plus 13 on 5. And my small y is going to be capital Y plus 9 on 5. And the same way, I'm going to change my dx dy. I'm going to change my dx dy to be the capital dy dx rather. My dy dx to be the capital Y over the capital X. So these are what we are going to substitute into our main differential equation. And in doing so, we are going to get something like this. X plus 13 on y on 5 minus 2 y capital Y minus 2 capital Y plus 9 on 5 plus 1 multiplying the capital X. And we have plus, my space is limited, 4x plus 13 on 5 minus 3y plus 9 on 5 minus 5, the capital Y equal to 0. So after that, we can, after doing your operations, your addition and subtraction, we are going to end up with x minus 2y dx plus 4x minus 3y dy being equal to 0. Okay. And after that, you can change it into separable. So here we've made it homogeneous. So now we can make it separable by letting capital Y be what? Capital X v. And we make dy, capital dy equal to x dv plus v dx. So I'll end the video here because we already know how to solve homogeneous differential equations. So I'll end the video here. Thank you all. Bye bye.